Hello everyone, welcome to this presentation called Shear Flow with Pressure Gradient for a Newtonian Fluid. My name is Hugo, and in the previous video we solved the simple shear flow, which is one of the easiest and simplest flows from which an analytical solution for the velocity profile can be obtained from solving the governing equations. So in this new video we will make the simple shear flow a bit more complex. So we will add an additional source of movement. So let me explain very quickly what was simple shear flow. So in the previous videos, we described a simple shear flow, which is the flow in which a fluid is contained. The fluid is here, over here. So the fluid is contained between two parallel plates, which is this one and this one. So these two plates are separated by a distance h. And also, at the bottom, this plate is fixed, so it's not going to move. And that means that the velocity here at the bottom is going to be equal to 0. On the other hand, the top plate is going to move with a velocity uv in x direction. So in simple shear flow, the layers of fluid that are very close to the top wall are going to move also with a velocity uv. And then the momentum, which, if you remember, momentum is defined as the product of the density of the fluid multiplied by the velocity of the fluid. The momentum is going to be transferred from top to bottom. So the velocity will vary in y direction. So this is our coordinate system, which is Cartesian. We have the x direction, we have y direction, and z direction. C is neutral directions, so nothing is going to happen in that direction. Also, the fluid layers that are here, the upper ones, will drag down the lower layers of fluids. So that means that the layer of fluid that is here is going to be dragged down by the upper layer. So let's call it 1, 2. There might be another 3 layer of fluid. So 3. So the layer of fluid number 1 is going to drag down the layer of fluid 2. And the layer of fluid 2 will have a lower value of velocity compared to 1. And then the layer of fluid number 2 will also drag down the layer of fluid number 3, and the velocity in the layer of fluid 3 is going to be smaller compared to the velocity at the layer 2, and so on. So that was for the case of simple shear flow. But now we will include a new source of movement. So that means that there is going to be some sort of mechanical device over here, which might be a pump. So this pump is going to push the fluid in this direction. So that means that the pump, the mechanical device, is going to add a new force, which is called the pressure gradient. So this pressure gradient means that we have a variation of the pressure in x direction. So this pressure gradient will push the fluid in this direction. So we have two sources of movement. So we have the velocity that is inducing the top plate over the fluid that is contained here, and then we have a force that is being applied to the whole bulk of fluid that will make the fluid flow in x direction. So let's mention some points to consider in order to find the velocity profile. So our goal in this video is to find the velocity profile. So that means that we need to solve the Navier-Stokes equations for this flow. So since let me mention some points to consider. So we will assume an incompressible Newtonian liquid. So that means that the fluid will follow Newton's law of viscosity, which, if you remember, it's this equation. So that means that the diffusive flux of momentum is going to be equal to the product of the viscosity multiplied by the gradient of the velocity. So this force is going to be applied over this surface, which will induce a flux of momentum that will be transferred from higher concentrations, because the momentum is going to be higher here at the top plate. So this momentum is going to be transferred from top to bottom. And incompressible means that the density is not going to depend on both, on either position and time. So we will also assume isothermal flow. So that means that the temperature is going to be constant. So there is not going to be any source of energy introduced into the system. So we will not introduce heat over the fluid. So in laminar flow, in the previous video, I explained the concept of laminar flow. So in laminar flow, the fluid elements will move in parallel layers without mixing. So that means that we will not have any mixing over here. Also the layers of fluid, which are these ones. So the fluid will move in x direction. So all the layers of fluid will move smoothly over one another, and fluid layers move along uniform and predictable paths. So for laminar flow, we have this condition. Laminar flow is observed when the Reynolds number, which is the product between the density, velocity, and height, which is this length, over the viscosity. So laminar flow is observed when Reynolds number is equal to 0. So that means we either have large values of viscosity, or we have small channels, low velocity values, or low density values. So in the case we have the opposite, which means a large Reynolds number. So for instance, when this is much larger than 1, we will have a very chaotic flow, unpredictable. The movement of the layers of fluids, or the fluid particles, will be unpredictable. So this is not the case. So we will be focusing when the Reynolds number is equal to 0. So that means low values of velocity, small channels, or high values of viscosity. So laminar, so this will simplify the solution of the problem. So we also assume a constant physical property. So that means that the viscosity and the density will be constant. And yeah, we have gravitational effects acting on the flow. So the gravitational field is always going to point out in y direction towards the bottom, downwards. So this is the gravity vector. So it will only have a non-zero contribution in y direction. So we will also assume a steady state. So that means that we will not care about the temporal terms of the equations. And also, it also means that the velocity will not depend on time. And as I said before, we have a constant pressure gradient acting in x direction. So this is going to be important to solve the equations. So this is, let me write it here, write it down. So this is going to be equal to a constant. And just very quickly, the only non-zero element, the non-zero component of the velocity field, is going to be the velocity in x direction, because this is a very well-controlled flow. So there will not be variations of velocity in either y or in C. So the only movement of the fluid will be happening in X direction. So that's why we also have this velocity field. So we need to find Ux, an equation for Ux. So now boundary conditions. So these boundary conditions for this problem are actually the same compared to the simple shear flow, because the pressure gradient is only going to be a source term. So we will include including a new source of movement into the flow. So the boundary condition for this system is that at the top plate we have at the bottom plate we have non-slip boundary conditions. So that means that the velocity when y is equal to 0, the velocity is going to be 0, which is the condition we specify here. Now at the top plate, which is here, when y is equal to h, the top plate is going to move with a velocity uv. So that means that ux when y is equal to h is going to be uv. So we will use these values later. And now let's solve the Navier-Stokes equation. So first we have the continuity equation in Cartesian coordinates. So this is the simplified form of the Navier-Stokes equation. So if you remember that we specify that we will only have a non-zero component of the velocity field in x direction. So that means that ux is not going to be 0, but on the other hand, uy and uc are going to be 0. So these derivatives are 0. So we end up with this equation, which tells us, this equation is telling us that if this derivative is 0, so that means that ux is not going to depend on x. So that's the main conclusion that we can obtain from the continuity equation. And now let's solve the momentum conservation equations. So this is remember that the momentum conservation equation is actually a system of 3 partial differential equations, one for x, one for y, and one for c. So I already wrote down these equations to save some time. So now let's simplify all these terms of the equation in x direction. So you remember that we say that we will assume a steady state, so the velocity is not going to depend on time, or we don't care about the temporal behavior of the system. So this derivative is going to be equal to 0. So ux is actually different than 0, but you remember from the continuity equation, ux is not going to depend on x because this derivative is 0. So we have this derivative, so this is 0. So ux is going to depend on y because, as I said before, the velocity will vary in y direction because momentum is being transferred from top to bottom, but uy is 0 because of what we discussed here. So this term is 0, and the same similarly also uc is going to be 0 because of what we specified here, but also ux is not going to depend on c because c is the neutral direction and nothing is happening over there. So this whole term is 0. So we have here the pressure gradient in x direction. So you remember that this is constant because it's the mechanical force that we are imposing on the flow. So this is not going to be 0. So ux, if the first derivative of ux with respect x is equal to 0, so that also the second derivative is going to be 0. Ux is going to depend on y, so this is non-zero. and ux is not going to depend on c. So this is 0, and then the gravity does not act on x direction. So this derivative is 0. So what do we have now? So we have the following equation. So 0, all the left hand side is going to be equal to 0. So this is equal to the pressure gradient, which is constant, plus the viscosity multiplied by the second derivative of ux in y direction. So this is our simplified system. Now let's let's simplify the equation in y direction. So we do not care about temporal term, but also uy is 0. So because remember, our velocity field is going to be given by this vector field. So uy is 0. So this whole term is 0. Ux is different than 0, but uy is 0. So this derivative is 0. Uy is 0, and the derivative of uy with respect y is also 0. Uc is also 0, and also uy is 0. So this is all 0. So we do not know the exact value of the variation of the pressure in y direction. So we leave it here. Uy is 0. Also all those terms are 0. But this term is not 0 because the gravity is acting in y direction. So we have this equation. And gy is actually minus g. So this full equation, no. So this is an equation, a very famous equation in fluid mechanics, which is called the hydrostatic equation. So this is just simply a force balance. Remember, momentum conservation equation is based on Newton's second law. So here we have two forces. So we have the gravitational force, which is this term, and also here we have a force associated to the pressure. So the pressure might vary in y direction. So the gravitational forces, if the acceleration of the fluid is 0 in y direction, but we have a non-zero contribution from the gravitational forces, so we need another force that balances the gravitational force. So that force is this pressure gradient in y direction. So now let's solve the C component. I also just want to say that yes, this is a pressure balance in the vertical direction. But now let's go back to the C component. So again, this is even easier because the majority of the terms are going to be 0, because UC is going to be 0, this is 0, 0, 0. We do not know the value of this term because we don't have enough information. So ut is going to be 0, 0, 0, and we do not have a contribution from the gravity in c direction, so this is 0. So the only left term is this term, which just tells us that the pressure is not going to vary in C. So now let's write down a summary of what we have so far. So we have in x direction we have this equation, which I'm going to copy. I'm going to write it down here. In y, we have the hydrostatic equation, which is this one, which is a balance of forces in vertical direction. And then in C, we obtain this equation that is telling us that the pressure is not going to vary in C direction. So this is our system of equations, simplified system of equations. So remember, this term is going to be constant. So that means that we have a decoupled system of equations. That means that we do not need to solve, we do not need an equation for pressure in order to find the velocity field in x direction, because this term is going to be constant. So, so yeah, that's basically what we have. So also the pressure is going to vary in three directions, no, in x and y, but we do not care about the pressure term. We need to find ux, so we need to solve this equation, which is a second order ordinary differential equation because ux only depends on y. So let's solve this equation using standard methods of ordinary differential equations. So once again, let's mention quickly, let's remind you that dp dx is going to be equal to a constant. So let's call it, no, let's call it that this is going to be a constant. So 0 is equal to minus dp dx plus viscosity. And now this is an ordinary differential equation. So let's solve this equation. So now let's pass this term over here. So we have something like this. Now let me pass the viscosity over here. So we have 1 over viscosity multiplied by the gradient pressure, the pressure gradient. And now let's split this variable, this derivative, as follows. And now this derivative can be passed to the right hand side. And now we just integrate this equation. So ux so yeah, so this is constant. This is why it's out of the derivative. So we have something like this. So we integrate the right hand side, and then we have our first constant of integration. So I made a mistake here. So this has to be actually here, because we pass the derivative to the right hand side. So we have the differential of this gradient. And now, yeah, it's fine. So this integral is just simply expressed as this. So we have our first constant of integration. And now let's do something similar. So we will pass this differential to this side. No. So we have 1 over viscosity multiplied by the pressure gradient dy. So we have this whole equation, which we integrate again. And now this first integral is ux is equal to 1 over u mu. So you remember the integral of y with respect the differential of y is going to be half y to the 2, and then plus c1y minus c2. So we have our second integration constant. So we have found our velocity profile. Now we need to apply the boundary conditions to find those values of C1 and C2. So you remember that the value of velocity at the bottom plate, so that means when y is equal to 0, so the velocity is going to be equal to 0. So we applied this boundary condition into this equation. So ux is going to be equal to 0, and this is going to be equal to 1 over viscosity. No, I'm sorry, this is x, because yeah, it's here. So the gradient, the pressure gradient multiplied by half, multiplied by y to the 2, but y is 0, so this is 0, plus c1 multiplied by 0, because we have a y term, plus c2. So this term is 0, and this term is 0. So that means that c2 is going to be 0. Now at the top plate, so that means that the velocity when y is equal to h is equal to b, the value of the top plate, at the top plate, the value of the velocity at the top plate. So ux is going to be equal to b, and this is going to be equal to this whole equation, which is 1 over viscosity multiplied by the pressure gradient, multiplied by half, multiplied by y, but y is h, so h to the 2, plus c1 multiplied by y, but y is h because we are at the top plate. And remember, plus c2, but c2 is 0, so we do not include it. So now let's find the value of c. So c is going to be equal to b minus 1 over, because we are passing this whole term to the left, so that's why it's negative. And now c1 is just You can do the algebra and you will get the same result. So now let's substitute C1 into the original equation, which is this one. So Ux is going to be equal to 1 over viscosity multiplied by the pressure gradient multiplied by half multiplied by g to the 2 plus C1, but C1 is this whole term, this one. So I'm going to include it at the bottom. And then all of this multiplied by y, because it's here. Now let me rearrange this equation. So let's write it like this. Then we will, you can notice that here we have similar terms. So I'm going to arrange all these terms into a single term. So we will have something like this. Half, let me write it like this. So we have the pressure gradient, which is constant, you remember. And then we have something like this. So this is the velocity profile. So let me just do some very quick definition of a variable. So let's define this variable. So y over h, which is going to be within the domain 0 to 1. So when y is equal to 0, the y over h is going to be equal to 0, but when y is equal to 1, y over h is going to be equal to 1. So this is why it's defined here. So this whole equation can be written as this. I'm going to do some algebra, but I'm going to write straight the equation. So this is the velocity profile we were looking for. And if you watch the previous video, you will recognize that this term is the velocity profile we found for the simple shear flow case. And then we have a new contribution that comes from the pressure term, from the gradient pressure, which comes from this force that is being induced by our mechanical device, by our pump. So this is actually a very interesting solution because, as I said before, we have two sources of movement. We have a contribution from the movement of the top plate, which is moving with a velocity uv. But as I said before, we also have a contribution from the other source of movement, which is the pump. So we have some particular cases when the pressure gradient is 0. So this whole term is 0. So we have the simple shear flow solution. On the other hand, when the top plate is not moving. So before that, remember this is the solution of the simple shear flow problem. So remember that this is a linear term. So this is our bottom plate, which is fixed. at the top plate we have that the top plate is moving. So yeah, this is the velocity profile for simple shear flow, which means that the velocity at the upper layers is going to be higher compared to the layers of fluid that are at the bottom. And now what happens? So this is the particular case number 1. Now for the case 2, what happens when B is equal to 0? That means when the top plate is not moving. So we have a velocity profile contribution that comes from all this term, which is going to take this form. And you can recognize that this is a parabolic equation because we have a parabolic term. So the profile will look something like this. So this is our top plate, this is our bottom plate. So if we only have a contribution from the pressure gradient, the fluid profile will be parabolic. So it will look something like this. So we will have a maximum value of velocity at the central line. So when y is equal to half. So here y is equal to h, here y is equal to 0. So this is a parabolic profile, and this curvature is due to the viscous effects. So the Newtonian viscous effects are causing a decrease in the velocity towards the channel walls because there are energy losses due to friction, because there is going to be some friction here. So this is why it's parabolic. So this problem is very common in fluid mechanics. So this profile, you will always observe this profile when you only have an effect of the pump onto the flow. So what happens when we have both contributions, when B is different than 0, and then we have a pressure gradient constant? So the profile, the velocity profile, so remember here the velocity is moving, the top plate is moving in x direction. So the velocity profile will look something like this, some sort of semi-parabolic. So we have both effects. The drag that is caused by the top plate, that is making the fluid move in x direction, but also we have a contribution from the pump that is pushing the fluid in x direction. So the velocity profile will look something like this. So now let me define quickly this a new quantity. So we have something, this ratio, which is, it will look something like this. So this is actually a dimensionless ratio, because you obtain the dimensions of these both terms, you will notice that it will not have dimensions. So basically we are comparing two characteristic velocities: the velocity caused by the movement of the top plate, which is the one at the top, and then at the bottom we have the characteristic velocity due to the pump, due to the force that is pushing the fluid in x direction from our mechanical device. So yeah, if this value is much more smaller than 1, so the velocity contribution from the pressure is going to dominate. On the other hand, if this is much more bigger than 1, the contribution from the top plate, from the movement of the top plate, is going to dominate into the system. So you can vary these values of the velocities, of characteristic velocities, and then you will get some variation. So into the velocity profile, it could look something like this, but it could look something like this. So it will depend on the values you impose on the pressure gradient, but also on the velocity at the top plane. It will also depend on the channel size and also on the viscosity of the fluid. So with this, I conclude this presentation. So I wanted to solve these problems analytically, because though these are the simplest problems from which an analytical solution for the velocity profile can be obtained from the Navier-Stokes equations. And in the next videos, I want to give an introduction to two popular numerical methods that are used to solve the Navier-Stokes equations, which is the finite difference method and the finite volume method. So we will solve exactly the same problems we are solving here, but using numerical techniques. And then these equations that I obtain here will be used to compare the numerical solutions. We will compare the numerical solutions obtained from those numerical methods with the exact analytical solution for the velocity profile for this problem. So thank you everyone for staying here. So I will see you in the next videos.